Hello students, in this video we are going to see that how we can determine the HOMO and LUMO energies from cyclic voltammetry and absorption spectroscopy. Cyclic voltammetry or CV is very important in photovoltaics for the determination of LUMO and HOMO energy levels. Now what is LUMO and what is HOMO energy of a material? LUMO stands for the lowest unoccupied molecular orbital, such as you can see in this diagram. The upper energy level is the lowest unoccupied molecular orbital having no electrons. It's the lowest energy level which does not have any electrons. It is equivalent to the conduction band in semiconductor oxide materials. And for other molecules, it is usually termed as LUMO. But for semiconductor oxides and metals, it is termed as the conduction band of the material. HOMO or highest occupied molecular orbital is the highest orbital which has electrons in it. It is equivalent to the valence band in the semiconductor oxide materials or metals. Now these values of energies of the HOMO and LUMO, they can be determined from the reduction and oxidation potentials of the molecule, which in turn can be obtained from cyclic voltammetry. The equations that are used in this regard are E LUMO, energy of the LUMO, is equal to minus half-wave reduction potential plus 4.4 volts. Now here, E half-wave reduction potential is obtained from the cyclic voltammetry, as you will see in the next slide. 4.4 electron volts is 4 volts is the constant. Now after getting the E LUMO from this equation using cyclic voltammetry, we can determine the value of E HOMO by putting this E LUMO value here. E HOMO will be equal to the energy of the LUMO orbital minus E gap, which is determined from the optical absorption spectroscopy. E gap is actually the band gap of the material, and we will obtain it using the electronic absorption spectroscopy or UV visible spectroscopy. So here you use two techniques, the cyclic voltammetry here and optical absorption spectroscopy to determine the E gap of the material. And these two techniques will give you the values of E HOMO and E LUMO. Now let's see how we can do that. This is on this side of the slide. You can see the cyclic voltammogram of a compound of some kind of a porphyry. The cyclic voltammetry shows two peaks. Here you can see starting from here, this cyclic voltammogram is giving a cathodic peak. Cathodic peak because it's in the negative potential. So this is the cathodic peak. And on the reverse direction, it is also giving another peak which will be anodic peak because it's the oxidation of the reduced compound. So this one is the first cathodic peak and this one is the first anodic peak. Further, this CV also gives another second anodic peak. So we want to determine the half-wave reduction potential from this cyclic voltammetry. So what is the half-wave reduction potential? It is actually the mean value of E cathodic and E anodic. It is determined by determining the mean value of this peak potential and this peak potential, and that will give you the value of E half-wave reduction. By putting it into this equation, and the first equation, you will get the value of E LUMO, that is the LUMO energy of the molecule. Now, in order to find out the E HOMO, that is the HOMO energy of the molecule, we need to use another technique which is called as the UV visible absorption spectroscopy. Let's consider that this is the absorption spectrum of the same compound, and here you can see 4 peaks. Like the first one is the very intense peak, and you have 1, 2, 3 smaller peaks here. So what you have to do, you have to find out the peak position of the peak which is lying at the highest wavelength in the most bathychromically shifted peak. So this one is the peak which lies in the most red region, having the highest wavelength, and if you enlarge this spectrum, you will see that this is the peak here. You can take the wavelength of this peak, the maximum wavelength, or sometimes you also take the edge of this peak having the maximum wavelength. So you get the wavelength from this position, from either the peak position or the edge of this highest wavelength peak. So what you do, you convert this wavelength into the electron volt, that is the band gap, and this can be done by using a simple relationship which is given here, 1:40 divided by wavelength. This wavelength is obtained from the peak position here, and after doing this calculation, I get the band gap of 2.1 electron volt. Now I can put this band gap here in this equation. E LUMO I have already calculated from CV, and I can determine the value of the E HOMO from this equation. So here you use two techniques, the cyclic voltammetry of the compound and the absorption spectroscopy of the compound, to find the energies of the HOMO and LUMO orbital. So thank you. If you like this video, please like and subscribe my channel to get more updates and more videos. Thank you.